Good evening, and welcome to The Sleepy Scientist. I'm very glad you've joined me tonight. Before we settle in, leave a comment and tell me where in the world you're listening from. I love seeing how far these evenings reach. Wherever that is, I hope you can get comfortable, whether you're tucked into bed, lying somewhere quiet with the lights low, or letting this play as the evening slips away. Relax, and give your mind permission to wander for a while. If these slow journeys through science are something you enjoy, leaving a like and subscribing is a simple way to support the channel and help these videos reach a few more sleepy minds. If you're already subscribed, thank you for continuing to spend part of your evenings here. It means a great deal. And we're now uploading episodes to Spotify, so if you'd rather turn the screen off and simply listen, there's a link in the description. Close your eyes if you like. I'll carry on regardless. Tonight we're going to explore something you experience every second of your life, yet physics still struggles to fully explain. I'll do my best not to make it so fascinating that you suddenly decide sleep can wait. Although if you do find yourself staring at the ceiling, wondering why broken glasses never rebuild themselves, or why you can remember yesterday but not tomorrow, I'll have to take some of the blame. Because according to many of the fundamental laws of physics, there is surprisingly little preventing the universe from running backwards. And yet it never seems to. So why does time only move forward? A glass slips from your hand and falls to the floor. For a fraction of a second, there is still a perfectly ordinary drinking glass moving downward through the air. Then it strikes the ground, and suddenly there are fragments scattered in different directions. You have probably never wondered whether those fragments might eventually leap from the floor, fly back together, seal every crack, and return neatly to your hand. The answer seems obvious. That simply does not happen. Smoke escaping from a candle spreads through the room. It does not normally gather itself back into a thin stream and disappear into the wick. Cream poured into coffee swirls through the liquid until the two become mixed. It does not patiently separate itself again. An ice cube dropped into warm water melts, and the water does not spontaneously reorganize itself into exactly the same cube. Even our own bodies seem to obey this direction. Wrinkles appear, cells accumulate changes, scars remain after injuries have healed. We grow older rather than younger. Everywhere we look, nature appears to know which way time is supposed to go. And yet, rather strangely, many of the fundamental laws used to describe nature do not contain anything so obvious. This is where the puzzle begins. Imagine recording a simple pendulum swinging from side to side. If you played the recording backwards, there might be nothing immediately suspicious about it. The pendulum would still swing. It would still slow near the ends of its motion and speed up as it passed through the middle. Under idealized conditions with no friction, the reversed motion could be just as compatible with the equations of mechanics as the original. Now record a glass falling from a table and shattering. Reverse that film, and the illusion disappears immediately. Pieces of glass slide across the floor, leap upward, assemble themselves perfectly, and rise into the air until an intact glass settles gently onto the table. You would know within seconds that the film was running backwards. That difference points towards something physicists call the arrow of time. The arrow of time is not simply the feeling that time is passing. It is the physical distinction between directions in time. It describes why processes throughout the world develop one way rather than the other, even when the microscopic laws beneath them often allow both directions. The most important of these arrows is the thermodynamic arrow of time. Thermodynamics is the branch of physics concerned with heat, energy, temperature, work, and the collective behavior of enormous numbers of particles. Within thermodynamics, the direction of time is closely associated with a quantity called entropy. For an isolated system, entropy is overwhelmingly likely to increase. That sentence sounds simple, but it carries an extraordinary amount of physics inside it. Entropy is often described casually as disorder, although that description is incomplete. More precisely, entropy is related to the number of microscopic arrangements that are compatible with the large-scale state we observe. A neatly separated system often corresponds to relatively few possible microscopic arrangements. A thoroughly mixed system can correspond to enormously more. Cream concentrated in one region of a cup has fewer compatible arrangements than cream dispersed throughout the coffee. Gas confined to one side of a container has fewer accessible arrangements than gas spread throughout the entire volume. Once a system moves from a relatively unusual arrangement into one that can be realized in vastly more ways, there is no mysterious force preventing it from going backwards. The reversed behavior is simply fantastically unlikely. This thermodynamic arrow appears to sit beneath many other arrows that surround us. There is a psychological arrow associated with memory. We remember earlier events but not later ones. There is a radiation arrow. Light and other forms of radiation are normally observed spreading outward from sources rather than converging from every direction into them. There is a causal arrow. Causes appear before their effects. There is a biological arrow. Organisms develop from young states into older ones, carrying records of their previous history. Quantum physics introduces questions about whether measurement and the loss of observable quantum coherence also possess a preferred direction. And on the largest scale of all, the universe itself has a cosmological arrow associated with its expansion from a much hotter and denser early state. These arrows seem remarkably well aligned. But describing that alignment is not the same as explaining why it exists. Physics has become extremely good at describing how irreversible behavior emerges once certain starting conditions are given. Statistical mechanics can explain why gases spread out, why heat moves from hotter regions toward colder ones, and why macroscopic objects almost never reconstruct themselves from their fragments. The deeper difficulty lies further back. Why were the starting conditions of the universe suitable for entropy to rise at all? The early universe appears to have occupied an extraordinarily special state. Although it was hot and dense, it was also remarkably smooth on large scales, especially in its distribution of matter. Once gravity is included, this smoothness corresponds to enormous potential for entropy to increase as matter later collapses into stars, galaxies, galaxy clusters, and black holes. So the mystery of time reaches all the way back toward the beginning of the observable universe. It is not merely a question about clocks. It is a question about why evidence accumulates behind us rather than ahead of us. Why footprints record where someone has been rather than where they are going. Why photographs preserve earlier moments. Why causes leave effects. Why memories point in one direction. And why the physical world repeatedly moves from states compatible with relatively few microscopic arrangements toward states compatible with enormously more. The strange part is that the underlying laws often seem far less concerned about direction than the world they produce. Somewhere between the reversible equations of microscopic physics and the irreversible reality of everyday life, an arrow appears. We know a great deal about how that arrow behaves. What remains much harder is explaining why it points the way it does. If shattered glass, spreading smoke, and melting ice all seem to know which direction time is supposed to move, it is natural to wonder whether that instruction is somehow written into the microscopic laws beneath them. Perhaps every molecule carries a tiny preference for the future. Perhaps every atom is nudged in one temporal direction. Perhaps the equations themselves contain some hidden sign saying that one way is allowed and the other is forbidden. For much of physics, however, that is not what we find. Imagine two perfectly smooth billiard balls moving across an ideal table with no friction. They collide, change direction, and continue on their way. If you recorded the collision and played the film backwards, the reversed motion could look entirely reasonable. The balls would approach along the paths they originally left on, collide at exactly the same point, and depart along the paths from which they originally arrived. Nothing in that reversed sequence obviously violates the laws of mechanics. This property is called time reversal symmetry. It does not mean that physicists literally turn a clock backwards. Instead, it means taking a physical process and constructing the appropriate reversed version of it. Velocities change direction. Momenta reverse. Other quantities that depend on direction, including magnetic effects and certain properties of quantum states, must also be transformed correctly. When all of that is done, many fundamental equations continue to describe a perfectly valid physical process. This is already present in the classical mechanics developed by Isaac Newton. Newton's laws describe how forces change the motion of objects. Under many ordinary conditions, if one solution to those equations describes a collection of objects moving forward through time, then reversing all their velocities produces another mathematically allowed solution that retraces the motion. A planet orbiting a star provides a useful example. Imagine an idealized planetary system in which every object suddenly had its velocity reversed with perfect accuracy. The planets could, in principle, retrace their previous orbits. The equations do not complain. They do not contain a rule saying that the planets are now travelling the wrong way through history. Something similar appears in electromagnetism. During the 19th century, James Clerk Maxwell brought electricity and magnetism together into a unified theory. Maxwell's equations describe electric fields, magnetic fields, and electromagnetic waves, including light. We normally encounter electromagnetic radiation spreading outward from a source. Switch on a lamp, and light travels away from it. A radio transmitter sends electromagnetic waves outward through space. But the underlying theory also allows appropriately constructed reversed solutions in which electromagnetic radiation converges inward. An enormous collection of precisely coordinated waves could, mathematically, arrive from different directions and converge upon a source in the reverse of an ordinary emission process. We almost never see anything like this happening naturally, of course. But that difference between what the equations allow and what the universe actually tends to do is precisely the problem. Even gravity does not obviously rescue us. Albert Einstein's general theory of relativity describes gravity as the curvature of spacetime produced by matter and energy. Its equations can describe evolving universes, orbiting objects, gravitational waves, collapsing stars, and black holes. Yet the theory does not simply contain a universal switch identifying one thermodynamic direction as the future. Spacetime can possess causal structure, distinguishing which events can influence which others, but that is not the same thing as explaining why entropy consistently increases in the direction we call the future. Quantum physics brings another version of the same puzzle. The evolution of an isolated quantum state is described by the Schrödinger equation. This evolution is unitary, meaning that quantum information is preserved in the ideal mathematical description. Under the appropriate transformation, this evolution is reversible as well. If the exact quantum state of an isolated system were known, the equations do not require its information simply to vanish as time passes. That can sound deeply unlike the world around us. A cup of hot tea cools. Perfume diffuses across a room. Your breakfast does not politely unmix itself a few hours after you have eaten it. The difficulty lies in scale and information. A macroscopic object contains an astonishing number of microscopic degrees of freedom. Even a tiny amount of ordinary matter can contain numbers of atoms comparable to hundreds of billions of trillions. To reverse the complete behavior of such a system, it would not be enough to push a button marked backwards. The motion of essentially every relevant particle would have to be transformed with extraordinary precision. Their velocities, positions, correlations, electromagnetic interactions, and interactions with the surrounding environment would all matter. A single uncontrolled collision with an air molecule could spoil the reversal. For something as complicated as a shattered glass, the required microscopic coordination would be so fantastically precise that the reversed event becomes practically unimaginable. This distinction is crucial. A process can be allowed by the underlying equations without being remotely likely to occur naturally. There is also one important qualification. Nature is not perfectly time reversal symmetric in every known interaction. Processes involving the weak nuclear interaction display genuine violations of time reversal symmetry. Experiments involving unstable subatomic particles have shown that certain microscopic transformations distinguish between temporal directions. This is real fundamental physics, but it does not provide a straightforward explanation for the arrow we experience every day. Weak interaction time asymmetry does not explain why ice melts into warm water and refuses to reconstruct itself. It does not explain why smoke disperses, why organisms age, or why memories contain records of yesterday rather than tomorrow. Those everyday asymmetries remain overwhelmingly thermodynamic, so physics presents us with an unusual situation. At the microscopic level, much of the machinery of nature is either reversible or extremely close to it. At the macroscopic level, the world appears relentlessly one-directional. The laws can often describe both the film and its reverse. Reality somehow keeps choosing one of them. For all the strange reversibility hidden inside the fundamental laws of physics, the everyday world has always seemed much less willing to cooperate. Heat, in particular, behaves as though it has a preferred direction. Place a hot cup of tea in a cool room, and the tea slowly loses heat to its surroundings. Leave an ice cube on a warm plate, and energy flows into the ice until it melts. Put a hot metal object beside a colder one, and, given enough time, their temperatures move toward one another. What we do not see is the opposite happening spontaneously. A lukewarm cup of tea does not suddenly pull heat from the surrounding air and become piping hot while the room becomes slightly colder. Melted ice does not normally surrender its thermal energy to the kitchen and reconstruct itself into a frozen cube. This obvious direction in the behavior of heat became one of the first major clues that something important was missing from purely mechanical descriptions of nature. During the 19th century, the practical problem of building better engines forced physicists to confront it. One of the central figures was the French engineer and physicist Sadi Carnot. Steam engines were becoming increasingly important, converting heat from burning fuel into mechanical motion. Engineers naturally wanted to know how efficiently this could be done. Could a sufficiently clever engine convert all the heat supplied to it into useful work? Carnot discovered that there were fundamental limits. An engine requires a temperature difference. Heat enters from a hotter reservoir, some of that energy can be converted into useful mechanical work, and the remaining heat must ultimately be transferred to a colder reservoir. No amount of perfect engineering can completely remove this requirement. Carnot originally developed these ideas before physicists had a modern understanding of energy conservation, but his work became one of the foundations of thermodynamics. The first law of thermodynamics describes the conservation of energy. Energy can change form. Chemical energy can become heat. Heat can become mechanical motion. Electrical energy can become light. But in an isolated system, the total amount of energy is conserved. At first glance, this might seem sufficient. If energy is conserved, perhaps everything about heat should follow from that principle alone. But conservation of energy tells us nothing about direction. Imagine heat flowing spontaneously from a cold object into a hotter one. The colder object loses a certain amount of thermal energy, and the hotter object gains exactly the same amount. Energy has still been conserved. The first law, therefore, does not forbid this process. Yet in ordinary circumstances, it simply does not happen. Something else is needed. That something became the second law of thermodynamics. Rudolf Clausius was one of the scientists who gave the second law a precise form. His formulation can be expressed very simply. Heat does not spontaneously flow from a colder body to a hotter body without some other physical change occurring elsewhere. That final qualification matters. It is perfectly possible to move heat from somewhere cold to somewhere warm. A refrigerator does exactly that. Inside a refrigerator, heat is removed from the cold interior and released into the warmer room outside. But the refrigerator requires electrical energy to operate its compressor and other components. It does not move the heat for free. In fact, the refrigerator releases more heat into the room than it removes from its interior, because the electrical work supplied to the machine ultimately becomes heat as well. So the second law remains intact. William Thomson, who later became known as Lord Kelvin, expressed the same underlying principle in another way. No cyclic heat engine can take heat from a single reservoir and convert all of it into useful mechanical work while producing no other effect. Some energy must ultimately be transferred as heat to something else. This is why even an ideal heat engine cannot be perfectly efficient. The second law does not say that energy disappears. The first law forbids that. Instead, it says that the usefulness of energy changes. Energy concentrated in a temperature difference can perform work. Once that energy has spread more evenly through the surroundings, the same total amount of energy may still exist, but less of it is available for useful conversion. Clausius introduced a quantity that helped describe this direction systematically. He called it entropy. Entropy is a property of the state of a physical system. In a reversible ideal process, the total entropy of an isolated system remains unchanged. In an irreversible process, total entropy increases. The distinction between reversible and irreversible processes is important. A perfectly reversible process is an idealization. It occurs infinitely gently, without friction, turbulence, uncontrolled heat flow, or other dissipative effects. If every step were reversed, both the system and its surroundings could, in principle, return exactly to their initial conditions. Real processes are almost never so obliging. Friction converts organized motion into heat. Electrical resistance produces heating. Viscosity dissipates organized fluid motion. Turbulence transfers energy through complicated patterns until it is ultimately degraded into microscopic thermal motion. Chemical reactions can proceed strongly in one preferred direction under particular conditions. Diffusion spreads particles from concentrated regions into less concentrated ones, and heat naturally flows across a temperature difference from hotter regions toward colder ones. All of these familiar processes generate entropy. The second law therefore gave physics something that the basic mechanical laws had seemed reluctant to provide. It gave nature a direction. But there was an uncomfortable problem hiding underneath. Newtonian mechanics had not suddenly stopped being reversible. The molecules in a hot gas were still obeying microscopic laws that appeared capable of running backwards. Thermodynamics could tell scientists with extraordinary reliability which macroscopic processes would occur and which ones would not. What it could not yet explain was why. Somehow, countless reversible microscopic motions were combining to create a world filled with irreversible events. And to understand how that could possibly happen, physicists had to stop looking only at heat and begin counting the hidden arrangements of matter beneath it. The second law of thermodynamics had given physicists a remarkably reliable description of what heat and matter tend to do. But describing a rule is not quite the same as explaining where it comes from. That deeper explanation began to take shape through the work of Ludwig Boltzmann. Boltzmann believed that the familiar properties of matter, such as temperature and pressure, could ultimately be understood through the motions of enormous numbers of atoms and molecules. At the time, the atomic picture of matter was still debated, but Boltzmann treated atoms as physically real and asked a powerful question. What happens when we stop following every individual particle and instead look at the collective behavior of trillions upon trillions of them? To answer that, it helps to separate two different ways of describing the same physical system. A macrostate is the large-scale description. If you have a container filled with gas, its macrostate might be described by quantities such as temperature, pressure, volume, and density. You do not need to know what every individual molecule is doing. You only need the overall properties that can be measured from the outside. A microstate is far more detailed. In classical physics, a complete microstate specifies the position and momentum of every particle in the system. For a container holding an ordinary amount of gas, that means an almost unimaginable quantity of information. Now imagine a box divided into two equal halves by a removable partition. Suppose all of the gas molecules begin on the left-hand side. That is an unusual macrostate. We can describe it very simply by saying that the gas is confined to half of the available volume. But even within that one macrostate, the individual molecules could be arranged in an enormous number of different ways. They could occupy different positions, move at different speeds, and travel in different directions while still remaining entirely on the left. Remove the partition, and the gas begins spreading through the whole box. Eventually it becomes roughly uniform. The gas has now reached another macrostate, one in which the density is approximately equal on both sides. The crucial insight is that this evenly spread state corresponds to vastly more possible microstates than the original confined state. Matter is not consciously trying to become more disordered. The gas does not know that it ought to spread out. There are simply enormously more ways for the molecules to be distributed throughout the entire box than for every one of them to remain crowded into one particular half. Boltzmann connected this idea directly to entropy. His famous relationship can be expressed in words as entropy equals Boltzmann's constant multiplied by the natural logarithm of the number of microscopic states compatible with the observed macrostate. The larger the number of compatible microstates, the larger the entropy. The logarithm in this relationship is not merely a mathematical decoration. It gives entropy an important property. If two independent systems are combined, the number of possible microstates multiplies, because every microscopic arrangement of the first system can be paired with every microscopic arrangement of the second. Taking the logarithm turns that multiplication into addition. So while the number of possible arrangements multiplies, the entropies of independent systems add together. This makes entropy behave in the useful way required by thermodynamics. Boltzmann's picture can also be understood through something called phase space. Phase space is an abstract mathematical space representing all the possible complete states of a system. For a single classical particle, its state depends on where it is and how it is moving. For many particles, the dimensionality of phase space becomes enormous. A particular complete microstate corresponds to one point in this vast abstract space. As the system evolves, that point traces a trajectory through phase space. Macrostates correspond not to single points, but to regions. A low-entropy macrostate occupies a relatively small region because comparatively few microscopic configurations satisfy its restrictions. An equilibrium macrostate occupies an overwhelmingly larger region because there are so many more ways for the system to look approximately uniform and balanced. This provides a statistical explanation for why equilibrium is so common. If a system begins in a small low-entropy region, its microscopic state evolves according to the ordinary laws of physics. There is no extra force pushing it toward equilibrium. But because the equilibrium region is so much larger, an ordinary trajectory leaving the low-entropy region is overwhelmingly likely to enter it. In that sense, entropy increase is not a command imposed on each particle. It is a statement about numbers. There are simply far more high-entropy possibilities available. Josiah Willard Gibbs later developed another powerful statistical framework using ensembles. An ensemble is a conceptual collection of many possible systems, each compatible with what is known about the macroscopic conditions. Gibbs entropy describes uncertainty across such a probability distribution over possible microscopic states, while Boltzmann entropy is more directly associated with the number of microstates belonging to a particular macrostate. The two approaches are closely related, but they answer slightly different questions, and beneath both of them lies the same extraordinary shift in perspective. Irreversibility could emerge statistically even when the underlying microscopic laws remained reversible. Yet there is an important catch. If every microscopic velocity in the spreading gas could somehow be reversed with perfect accuracy, the molecules could retrace their paths and gather back toward their earlier arrangement. The equations would still permit it. So Boltzmann had explained why movement toward higher entropy is overwhelmingly typical. But the microscopic trajectory itself had not become fundamentally one-directional. The asymmetry came from probability, from the way macroscopic states group together enormous numbers of microscopic possibilities, and most importantly, from the fact that the system began in an unusually restricted state. That final point would eventually become one of the deepest problems in the physics of time. Because once entropy increase depends on beginning somewhere special, the obvious question becomes impossible to avoid. Why was the universe ever in such a special state in the first place? Entropy is often introduced with a single word. Disorder. It is easy to see why. A tidy room becomes messy. A carefully arranged pile of papers spreads across a desk. A glass falls, shatters, and leaves fragments scattered across the floor. In each case, the later state looks less organized than the earlier one. So it is tempting to imagine that the second law of thermodynamics is simply telling the universe to become messier. But that is not really what entropy means. The word disorder can be useful as a loose analogy, especially when first encountering the idea, but it quickly becomes misleading if we treat it as a precise physical definition. Entropy is not a measure of how untidy something looks. It is connected to how many microscopic configurations are compatible with the macroscopic information we have about a system. Imagine a deck of playing cards. If the cards are arranged neatly by suit and value, We might call the deck ordered. Shuffle it thoroughly, and we would probably call it disordered. But from the perspective of microscopic specificity, every exact arrangement of the deck is equally particular. A perfectly sorted deck is one precise sequence. A shuffled deck is also one precise sequence. Neither individual arrangement is inherently more random than the other simply because one looks more pleasing to us. The difference appears when we group arrangements into categories. There are very few arrangements that we would describe as perfectly sorted, but there are an enormous number that we would casually describe as shuffled. The distinction comes from the way many detailed possibilities correspond to the same broad description. That is much closer to how entropy works. Return to a gas inside a container. Suppose a partition keeps every molecule on the left-hand side. There are still countless ways for those molecules to move around while remaining on the left. They can have different positions, different speeds, and different directions. But once the partition is removed, the molecules can occupy the entire container. There are now vastly more possible positional arrangements available. An approximately uniform gas filling the whole box corresponds to an overwhelmingly greater number of microscopic configurations than a gas restricted to one half. This is why the gas spreads. It is not trying to become untidy, it is simply moving into regions of its possible state space that contain far more compatible arrangements. Entropy is also closely connected to the spreading of energy. A hot object placed beside a colder one contains a useful temperature difference. Energy can flow from the hotter object toward the colder one, and during that process there may be opportunities to perform work. Eventually the temperatures become similar. The energy has not disappeared. It has become distributed in a way that offers fewer accessible large-scale differences to exploit. But even describing entropy as energy dispersal must be done carefully. It is not always the whole story. Entropy can involve the distribution of particles, energy, momentum, internal states, and correlations among different parts of a system. What matters is the number of microscopic possibilities consistent with what can be observed macroscopically. This becomes especially interesting when gases mix. Imagine one gas filling the left side of a container and another gas filling the right. Remove the divider and the gases diffuse into one another. If the particles belong to genuinely different gases, the mixed state can correspond to more distinguishable microscopic arrangements than the separated state. But suppose the gas on both sides is exactly the same. Removing the partition does not create the same kind of physically meaningful increase simply by allowing identical particles to swap places. This issue is connected to what became known as the Gibbs paradox, named after Josiah Willard Gibbs. The paradox helped reveal that counting microscopic states requires care, particularly when particles are indistinguishable. The lesson is subtle, but useful. Entropy does not depend on whether something looks mixed to human eyes. It depends on which distinctions are physically meaningful. This is also why increasing entropy does not prevent beautiful structure from forming. Consider a crystal. When a liquid freezes into a crystal lattice, the atoms or molecules may become arranged in a highly regular pattern. Visually, the result looks more ordered. If entropy simply meant messiness, crystallization might appear to violate the second law. But the crystal does not form in isolation. As the material freezes, it usually releases heat into its surroundings. The entropy associated with the material itself may decrease under suitable conditions, while the entropy increase in the environment is larger. The total entropy still rises. A snowflake provides an elegant example. Its elaborate structure forms because water molecules arrange themselves into an ordered crystal as heat is released into the surrounding air. The same broad principle applies to much more complicated organized systems. Living organisms can grow, maintain intricate structures, repair damage, and reproduce without violating thermodynamics. They do so because they are not isolated systems. A living organism continually takes in relatively useful forms of energy and matter and releases heat and waste into its surroundings. Earth itself receives concentrated energy from the hot surface of the sun and eventually radiates energy back into space at a much lower effective temperature. That energy flow allows weather systems, ecosystems, chemistry, and life to maintain local structure while the entropy of the wider environment increases. Organization and increasing entropy are therefore perfectly compatible. Even equilibrium is often misunderstood. A system at equilibrium is not necessarily still. In a room filled with air at a uniform temperature, molecules continue racing around at hundreds of meters per second, colliding constantly with one another and with the walls. Microscopically, there is tremendous activity. What has disappeared are the large-scale gradients. There is no strong pressure difference pushing gas from one side of the room to the other. There is no major temperature difference capable of driving a heat engine. There is no obvious concentration gradient forcing particles to diffuse in one preferred direction. The system still moves. It simply has fewer useful macroscopic distinctions left to erase. And that is a much better way to understand entropy than imagining the universe becoming steadily messier. The arrow of time is associated with the fading of accessible differences. Hot and cold become more alike. Concentrated substances spread. Distinct distributions become mixed. Useful gradients diminish. The microscopic motion continues throughout, but more and more detailed arrangements become compatible with the same broad appearance. What we experience as irreversibility is not nature developing a taste for chaos. It is the overwhelmingly probable movement from rare macroscopic conditions towards states that can be realized in vastly more ways. The second law of thermodynamics is so reliable that it can easily sound like an absolute command. Entropy increases. Heat flows from hot objects toward colder ones. Gases spread out. Concentrated substances diffuse. Macroscopic systems move toward equilibrium. And for the enormous systems we encounter in everyday life, treating the second law as an unbreakable rule works extraordinarily well. But at its deepest level, statistical mechanics gives us a slightly more subtle picture. The second law is overwhelmingly probable. That difference matters. Imagine watching only a handful of particles moving inside a small box. Each particle travels, collides with the walls, changes direction, and collides with the others. With so few particles, noticeable fluctuations are common. For a brief moment, more particles might happen to gather on the left side than on the right. A little later, the imbalance could reverse. Nothing particularly mysterious has happened. Small numbers naturally produce visible statistical variation. Now increase the number of particles. Instead of 10, imagine 1,000. Then 1,000,000. Then trillions upon trillions. The random irregularities do not disappear at the microscopic level, but their effects become increasingly insignificant compared with the behavior of the whole system. This is why macroscopic matter appears so stable. A room full of air contains an enormous number of molecules, all moving rapidly and colliding continuously. In principle, there is nothing in ordinary molecular mechanics that absolutely forbids every air molecule from wandering into one small corner of the room at the same time. No invisible barrier prevents it. Every molecule is already moving randomly, and a particular sequence of collisions could theoretically produce such a configuration. but the number of microscopic arrangements in which the air remains spread throughout the room is unimaginably larger than the number in which almost every molecule happens to occupy one corner. So although the clustered state is possible in principle, its probability is so tiny that waiting for it would not be a sensible evening activity. For practical purposes, it never happens. This is the statistical power behind the second law. The law does not need every microscopic event to move neatly toward greater entropy. Individual particles can fluctuate in either direction. Small regions can temporarily behave in unusual ways. What matters is the collective behavior of enormous numbers of degrees of freedom. For many ordinary systems, the equilibrium macrostate occupies almost all of the accessible region of phase space. Phase space represents all the possible complete microscopic states available to the system. Low-entropy macrostates occupy comparatively tiny regions within it. Equilibrium occupies an overwhelmingly larger region. Once a system is allowed to evolve freely from an unusual low-entropy condition, almost every accessible direction through phase space leads into states that look more like equilibrium. This also explains why entropy can decrease locally without violating the second law. The cleanest statement of the law concerns the total entropy of an isolated system. A smaller part of that system may become more organized or move into a lower entropy state, provided the wider process produces enough entropy elsewhere to compensate. A refrigerator is an obvious example. The interior becomes colder and is maintained far from thermal equilibrium with the kitchen around it. But the refrigerator consumes electrical energy. Its machinery releases heat into the room, and the total entropy generated outside exceeds the local reduction associated with maintaining the cold interior. An air conditioner works in much the same way. Plants provide a more beautiful example. A seed develops into an intricate living structure containing organized tissues, specialized cells, chemical gradients, and stored information. That local organization does not violate thermodynamics because the plant is an open system. It receives energy, primarily through sunlight, exchanges matter with its environment, and releases heat. The total process produces entropy even while remarkable structure develops locally. The same principle applies to an embryo developing into an organism. Cells divide, differentiate, construct tissues, maintain chemical gradients, and build increasingly complicated biological structures. But metabolism constantly consumes free energy and releases heat and waste into the surroundings. Computers also create highly organized patterns of information while consuming electrical energy and dissipating heat. Anyone who has rested a laptop on their legs for too long has encountered that thermodynamic accounting in a fairly direct way. None of these systems escape the second law. They simply are not isolated. This is why the familiar phrase entropy always increases should be treated as a very useful macroscopic shorthand rather than the most precise possible statement. A more careful version is that the total entropy of a large isolated system is overwhelmingly unlikely to undergo any appreciable spontaneous decrease. The word overwhelmingly is doing a great deal of work. At very small scales, entropy fluctuations are not merely theoretical. Microscopic systems containing relatively few particles can temporarily move in directions that would look astonishing if enlarged to human size. Researchers can observe tiny fluctuations in which heat briefly flows opposite to its usual average direction, or entropy production becomes temporarily negative over short intervals. Such behavior does not overthrow thermodynamics. It reveals the statistical foundation underneath it. As systems become larger, substantial downward fluctuations in entropy become extraordinarily unlikely. The chance falls so rapidly that by the time we reach ordinary objects, the reverse process has effectively disappeared from experience. And yet this leaves a deeper difficulty untouched. Probability can tell us why a gas that begins confined to one side of a box is overwhelmingly likely to spread out. But imagine encountering the gas halfway through its evolution without knowing its history. The microscopic laws themselves can be run in either temporal direction. Statistical reasoning could suggest that a highly unusual non-equilibrium state is likely to evolve toward equilibrium on either side of that moment unless additional information about its boundary conditions is supplied. This was precisely the kind of difficulty that troubled Ludwig Boltzmann and his critics. The equations allow microscopic motion to be reversed. The statistical framework tells us that equilibrium is overwhelmingly typical. But our actual universe does not appear to sit at equilibrium, with entropy increasing away from the present in both directions. Instead, all the evidence points toward lower entropy in one direction only. The past. So probability explains an enormous amount about why irreversible behavior is reliable. But probability alone does not yet explain why the low-entropy side of reality is consistently behind us rather than ahead. That is where the arrow of time becomes much harder to dismiss as mere statistics. Ludwig Boltzmann's statistical explanation of entropy was powerful, but it also attracted a very sharp objection. One of the physicists who raised it was Johann Joseph Loschmidt. The problem he identified was simple enough to describe, but difficult enough to become one of the most famous challenges in the foundations of statistical mechanics. Imagine again a box containing gas. At first, every molecule is confined to the left-hand side. The partition is removed, and the gas begins to spread. Molecules collide with one another and with the walls. After a while, they fill the entire container more or less uniformly. Entropy has increased. So far, everything looks exactly as Boltzmann's statistical picture predicts. Now imagine something almost absurdly precise. At one instant, every molecule in the gas has its velocity reversed. A molecule moving upward now moves downward at exactly the same speed. One travelling toward the right now travels toward the left. Every momentum is transformed perfectly. If the microscopic laws governing all those collisions are reversible, something remarkable follows. The molecules should retrace their previous paths. Every collision would occur in reverse. Molecules that had scattered apart would meet again in exactly the right places and with exactly the right velocities. Little by little, the gas would gather back toward the left-hand side of the box. Entropy would decrease. Eventually, the original low-entropy state could be reconstructed. This is Loschmidt's reversibility objection. The challenge is not that such a reversal is easy to perform. It plainly is not. The challenge is conceptual. If the microscopic laws permit the gas to evolve from a concentrated state into an evenly spread state, and those same laws permit the exact reverse trajectory, then how can irreversible behavior be derived from reversible mechanics alone? The answer depends heavily on something that is easy to overlook. The reversed gas does not begin from an ordinary equilibrium condition. To an observer who only measures pressure, temperature, and density, it might look like an ordinary gas filling the box. Microscopically, however, it is extraordinarily special. The positions and velocities of the molecules contain incredibly precise correlations. Each molecule is moving in just the right direction, at just the right speed, so that all future collisions coordinate to reconstruct the earlier state. That is nothing like choosing a typical microscopic arrangement from among the immense number corresponding to equilibrium. Boltzmann's own work already contained an important clue to this distinction. He developed what became known as the H-theorem, intended to show how a dilute gas approaches equilibrium through molecular collisions. A crucial assumption in that reasoning is often called molecular chaos. The basic idea is that particles approaching a collision can generally be treated as sufficiently uncorrelated. Their incoming velocities are not carefully coordinated according to some enormous hidden plan. For a gas spreading naturally from an ordinary low-entropy state, this is a reasonable statistical approximation. But the perfectly velocity-reversed gas is completely different. Its particles contain precisely the correlations needed for the entropy-decreasing sequence of collisions. Molecular chaos no longer applies in the same way, so the reverse trajectory does not disprove statistical mechanics. Instead, it reveals just how unusual an entropy-decreasing trajectory must be. There are vast numbers of microscopic states corresponding to an ordinary equilibrium-looking gas. Only an extraordinarily tiny fraction contain the exquisitely arranged correlations required for the gas to spontaneously reconstruct a particular earlier low-entropy state. This distinction is crucial. Entropy decrease is not fundamentally forbidden, it is statistically exceptional. And for macroscopic systems, exceptional can mean so improbable that it is effectively never observed. Consider what would be required to reverse a warm everyday object. Even a very small object contains an enormous number of atoms. To make it retrace its thermodynamic history, one would need control not merely over its visible motion, but over the microscopic state of essentially every relevant particle. Positions would matter. Momenta would matter. Internal molecular motions would matter. Interactions with surrounding air would matter. Thermal radiation leaving the object would matter. Photons already travelling away into the environment would somehow have to be accounted for as well, and perfect reversal would have to include the surrounding world with which the object had become correlated. A single slight error could ruin the reconstruction. Collisions amplify small mismatches. In a gas, one molecule arriving at a collision with a slightly incorrect velocity changes the trajectory of another molecule. That altered molecule then participates in further collisions, spreading the discrepancy. Very quickly, the beautifully coordinated reverse motion dissolves back into ordinary statistical behavior. This is practical irreversibility. The reverse process is allowed by the equations, but arranging the necessary microscopic state is beyond realistic control. Loschmidt's objection, therefore, does not destroy Boltzmann's explanation. It sharpens it. Statistical mechanics can explain why entropy-decreasing behavior requires exquisitely special correlations, and why typical systems do not possess them. But another question immediately appears. Why are such special correlations absent toward the future, while the universe clearly contains special conditions toward the past? When we observe a gas spreading, we infer that it was previously confined. We do not normally infer that its molecules are secretly coordinated so that tomorrow they will all gather back into one corner. The distinction comes from what we assume about the boundary conditions of the system. We treat the past as containing an unusual low-entropy state, and the future as unconstrained. That assumption works extraordinarily well. But the microscopic laws themselves did not tell us to make it. Loschmidt had exposed the deeper problem. Reversibility means that the equations can accommodate entropy increase or entropy decrease. Probability explains why ordinary uncorrelated states evolve toward equilibrium. What it does not explain, by itself, is why the extraordinary special condition lies consistently behind us. The puzzle has simply moved. Instead of asking why matter obeys irreversible laws. We are now asking why the universe began with the kind of conditions that make irreversible behavior overwhelmingly likely in only one temporal direction. Loschmidt's objection showed that a gas could, in principle, retrace its microscopic history if every relevant motion were reversed with impossible precision. But another challenge soon appeared. This time the problem was not what would happen if someone deliberately reversed the particles. It was what might happen if an isolated system was simply left alone for long enough. The idea came from the French mathematician and physicist Henri Poincare. Poincare studied the long-term behavior of dynamical systems governed by deterministic laws. From this work came what is now known as the Poincare recurrence theorem. Under certain conditions, a finite and isolated system whose motion remains confined to a bounded region of its possible state space will eventually return arbitrarily close to a state it occupied before. The wording matters. The theorem does not necessarily say that every particle will return to exactly the same position with exactly the same momentum at one perfectly repeated instant. Instead, it says that the system can eventually come as close as desired to an earlier state, provided the relevant mathematical assumptions hold and enough time is allowed. At first, this seems almost harmless. Then consider what it means for thermodynamics. Imagine once again a gas initially confined to one side of a box. The partition is removed. The gas spreads throughout the container and reaches equilibrium. Entropy rises. If the system is truly isolated and satisfies the conditions required for recurrence, then after a sufficiently long time its microscopic state can eventually wander arbitrarily close to the state from which it began. The gas could become extraordinarily concentrated again. A state that appeared to have been lost forever would return. This caused another problem for Ludwig Boltzmann's explanation of irreversible behavior. The German mathematician Ernst Zermelo recognized the difficulty and used Poincare recurrence as an argument against the idea that entropy could simply increase forever as a consequence of ordinary mechanical laws. If the system must eventually return near an earlier low entropy condition, then entropy cannot rise monotonically for all eternity. At some point it must decrease. Once again, the microscopic laws seemed unwilling to provide the permanent one-way direction suggested by thermodynamics. Boltzmann's response was fundamentally statistical. The recurrence might be allowed, but the relevant waiting time could be absurdly long. For a macroscopic system containing an enormous number of particles, the number of possible microscopic configurations becomes almost incomprehensibly large. Returning close to one particular earlier low-entropy arrangement can therefore require a recurrence time that dwarfs any timescale encountered in ordinary experience. Not merely years, not merely the age of a human civilization, not merely the lifetime of a star. For realistic macroscopic systems, recurrence times can become so enormous that comparing them with familiar cosmological timescales almost stops being useful. A cup of coffee cooling on a table is not realistically going to wait until its microscopic motions happen to reconstruct the original temperature difference. A broken object is not going to reassemble itself before the stars burn out. A living body will not spontaneously return to an earlier biological state because some unimaginably rare molecular recurrence has finally arrived. The mathematics may permit behavior of this general kind under ideal conditions. That does not make it practically relevant. There is another important limitation. The Poincare recurrence theorem applies to systems satisfying particular assumptions. An ordinary object in the real universe is not perfectly isolated. It exchanges thermal radiation with its surroundings. Air molecules collide with it. Photons escape. Gravitational influences extend outward. Quantum interactions create correlations with the environment. Energy and information continually spread into degrees of freedom that are extremely difficult to include in any simple closed description. Even defining the correct complete system can become challenging. If you enlarge the boundary to include the room, then the room interacts with the building. Include the building, and it interacts with Earth. Include Earth, and radiation continues escaping into space. The neat mathematical model of a finite, bounded, isolated mechanical system is immensely valuable, but it should not be confused with a straightforward prediction that familiar objects will eventually rewind themselves. Still, recurrence cannot simply be ignored. Its conceptual importance remains. It tells us that irreversible macroscopic behavior should not be understood as a claim that every exact microscopic trajectory must experience endlessly increasing entropy forever. The underlying dynamics can allow fluctuations, reversals, and returns. Statistical mechanics is making a different kind of claim. It describes what overwhelmingly typical macroscopic systems do over physically relevant timescales. If a system begins in a low-entropy state, the vast majority of compatible microscopic evolutions carry it toward macrostates, representing enormously larger regions of phase space. Equilibrium dominates because there are so many more ways to be near equilibrium than to be far from it. Rare departures are not absolutely impossible. They are simply extraordinarily improbable for large systems. Poincare recurrence, therefore, does not make a cooling cup of coffee mysterious. The coffee cools because that is overwhelmingly typical behavior from the state in which it begins. The recurrence theorem instead exposes something deeper about the arrow of time. If the fundamental dynamics can eventually return a system toward earlier configurations, then the observed direction of time cannot simply be an eternal instruction embedded in every microscopic trajectory. Once again, attention is drawn toward the system's starting condition. Our accessible history does not look like a random moment selected from an eternal equilibrium fluctuation. We observe galaxies, stars, planets, living systems, chemical gradients, memories, and countless other structures that all point toward a past with lower entropy. The important question is therefore not whether an ideal isolated system might fluctuate back toward an earlier state after an inconceivably long wait. It is why the universe we actually observe begins, as far as our evidence can reveal, so far from equilibrium in the first place. Poincare recurrence leaves the second law extremely successful in practice, but like Loschmidt's reversibility objection, it removes one tempting escape route. The arrow of time cannot be explained merely by declaring that entropy has no choice but to increase forever. The microscopic laws are more permissive than that. The real mystery lies in why our particular history begins on such an unusual side of the possibilities. James Clerk Maxwell found one of the most elegant ways to expose the statistical nature of the second law of thermodynamics. He imagined a container of gas divided into two chambers by a wall. In that wall is a tiny door, and beside the door is an equally tiny being, intelligent enough to watch individual molecules as they approach. This creature later became known as Maxwell's demon. The name sounds rather dramatic for something whose main job is opening and closing a little door. But the thought experiment creates a surprisingly deep problem. Suppose the gas begins at the same temperature on both sides of the container. Temperature is related to the average kinetic energy of the molecules. Some molecules are moving faster than average, others are moving more slowly. Even when the gas has a stable overall temperature, individual molecular speeds vary continuously. the demon watches them. Whenever a particularly fast molecule approaches the door from the left, the demon allows it through to the right. Whenever a particularly slow molecule approaches from the right, the demon allows it through to the left. At other times, the door remains closed. Gradually, the faster molecules accumulate on one side, while slower molecules accumulate on the other. One chamber becomes hotter, the other becomes colder. The demon has created a temperature difference from a gas that began in thermal equilibrium. That is troubling. Under ordinary circumstances, temperature differences tend to disappear. Heat flows from hotter regions toward colder ones until equilibrium is approached. Maxwell's demon appears to reverse that tendency. It seems to take an equilibrium state and make it less uniform. The entropy of the gas appears to decrease. Once a temperature difference has been created, it could even be used to operate a heat engine and perform useful mechanical work. The demon would apparently have extracted useful energy from the random thermal motion of molecules without paying the normal thermodynamic price. If that really worked as imagined, the second law would be in serious difficulty. But Maxwell's purpose was subtler than simply trying to destroy thermodynamics. The thought experiment reveals that the second law is statistical. The molecules themselves do not obey a microscopic command forcing fast particles and slow particles to remain mixed. If something could identify their motions and sort them individually, the random microscopic fluctuations already present in the gas could be exploited. The obstacle is not that such configurations are mechanically forbidden. The obstacle is that ordinary macroscopic systems do not possess a convenient microscopic gatekeeper carefully selecting molecules one at a time. The demon therefore shifts attention away from matter alone. It makes information important. To open the correct door at the correct moment, the demon must know something about each approaching molecule. It must acquire information about the molecule's motion. It must use that information to make a decision, and somehow that information must be stored or represented physically. This connection became much clearer through the work of the Hungarian physicist Szilard. In 1929, Szilard developed a simplified version of the problem involving only one molecule. Imagine a box containing a single molecule bouncing around inside. A partition is inserted into the middle of the box, dividing it into two equal chambers. The molecule must now be on either the left side or the right side. An observer measures which side contains it. That single piece of information can then be used to extract work. If the molecule is on the left, the partition can be connected to a mechanism and allowed to move slowly toward the right as the molecule collides with it. The molecule expands into the full volume of the box. During that expansion, it can push the partition and lift a small weight. If the molecule began on the right, the same process can be arranged in the opposite direction. The crucial ingredient is knowledge. Without knowing which side contains the molecule, there is no obvious way to arrange the mechanism so that the random motion reliably performs useful work. Once the information is available, the thermal fluctuation becomes exploitable. Information begins to look like a physical resource. That creates a new question. Where is the thermodynamic cost? Perhaps it occurs when the demon observes the molecule. Perhaps it occurs when the information is stored. Perhaps it appears when the demon changes its internal state. Or perhaps the crucial cost comes later, when the demon needs to clear its memory so that it can repeat the cycle. This distinction matters because simply acquiring information does not necessarily require a fixed minimum amount of entropy production in every possible physical implementation. The deeper limitation emerges when a memory must be reset and reused. A demon that remembers every molecule forever would eventually require an ever-growing physical memory. A cyclic daemon must eventually return its own information processing machinery to a reusable state. The thermodynamic accounting therefore has to include the daemon itself. It is not enough to examine only the gas. Modern experiments have created physical systems that behave in ways reminiscent of Maxwell's daemon. Researchers have used feedback to measure microscopic systems and then exploit the acquired information to extract work or influence fluctuations. Related demonstrations have been performed with classical particles and with controlled quantum systems. These experiments do not overthrow the second law. Instead, they confirm the deeper lesson hidden inside Maxwell's imaginary creature. When information, measurement, feedback, memory, and the physical machinery performing them are included in the accounting, thermodynamics survives. And this matters for the arrow of time, because the world is filled with information. Photographs store records, brains form memories, computers write data, particles become correlated through interactions, physical events leave traces in their surroundings, so any complete explanation of irreversibility must account for more than the spreading of heat and the motion of molecules. It must also explain how information is created, stored, used, and erased. Maxwell's daemon does not defeat the second law. It reveals that the second law reaches deeper than heat. It reaches into the physical nature of information itself. Maxwell's daemon forces us to take information seriously as part of the physical world. The tiny gatekeeper appears to reduce entropy by observing molecules, remembering what it sees, and using that knowledge to sort fast particles from slow ones. But if the daemon is a physical object rather than a magical one, then its memory must also obey the laws of physics. This became especially clear through the work of Rolf Landauer. In 1961, Landauer argued that information is not something floating freely above matter. Every stored piece of information must be represented by some physical state. A bit inside a computer might be represented by an electrical charge, a magnetic orientation, a voltage, the position of a microscopic component, or some other distinguishable physical condition. The information may be abstract, its storage is not. Landauer focused on an operation that seems almost trivial: erasing information. Imagine a memory containing one classical bit. It can be in one of two possible logical states. Now suppose we want to reset that memory so that, whatever its previous state happened to be, it always finishes in the same standard blank state. That operation destroys a distinction. Before the reset, two logical possibilities existed. Afterwards, both possibilities have been compressed into one. Landauer showed that this logically irreversible operation has a minimum thermodynamic cost. In words, the relationship is: the minimum heat released when one classical bit is erased equals Boltzmann's constant multiplied by the temperature multiplied by the natural logarithm of 2. At ordinary temperatures, the amount of energy associated with erasing a single bit at this theoretical minimum is extraordinarily small, only a few sextillionths of a joule. For one bit, it is barely imaginable. Conceptually, however, the significance is enormous. Information processing and thermodynamics have become connected. The reason is not simply that computers become warm. The deeper issue is what happens to the distinction between the possible states of the memory. If a memory could initially contain either of two values, and both are forced into the same final state, information about which state existed before has been discarded. In a complete physical description, that distinction cannot simply disappear without consequence. It is transferred into microscopic degrees of freedom in the surroundings. The environment becomes slightly less constrained. its entropy increases. This also reveals an important subtlety. Not every act involving information automatically carries the same minimum thermodynamic cost. Measurement is not identical to erasure. Storing information is not identical to erasure. Moving information from one physical location to another is not identical to erasure. And in principle, some logical operations can be performed reversibly. This distinction was explored in detail by Charles Bennett. Bennett showed that computation does not fundamentally need to destroy information at every step. A calculation can, in principle, be arranged so that its logical history is preserved and its operations can be reversed, instead of repeatedly throwing information away. A reversible computer can retain enough of its previous state to reconstruct the calculation backwards. That does not mean real computers operate without producing heat. They certainly do not. Modern processors contain enormous numbers of components switching states at extraordinary rates, with electrical resistance, leakage currents, imperfect control, communication between components, and many other dissipative processes. Real machines operate far above Landauer's theoretical minimum. The importance of reversible computation is more fundamental. It shows that the unavoidable thermodynamic cost is associated specifically with logically irreversible operations such as erasing information, rather than with computation as an abstract activity. Now, Maxwell's demon can be reconsidered. Each time the demon observes an approaching molecule, it gains information. Fast molecule, slow molecule, coming from the left, coming from the right. That information allows the demon to decide whether to open its door. Using feedback, it can convert microscopic thermal fluctuations into useful work and reduce the entropy of the gas. But the demon cannot simply keep collecting information forever if it is meant to operate as a repeating machine. Its memory would eventually fill. To begin another cycle in the same condition, the memory must be reset. Old records have to be cleared. And that reset produces entropy. When the complete system is considered, including the gas, the demon, its memory, and the environment receiving the waste heat, the apparent violation disappears. The entropy reduction achieved through sorting is compensated by entropy generated during the full information processing cycle. The second law survives. This idea has moved far beyond thought experiments. Researchers have tested Landauer's principle using microscopic physical systems in which individual information states can be controlled with remarkable precision. Experiments involving colloidal particles have represented bits using particles trapped in carefully shaped energy landscapes. Electronic systems have allowed information erasure to be studied through controlled electrical states. Quantum experiments have explored how the same thermodynamic principles operate when information is stored in quantum systems. Individual trapped atoms have even been manipulated in experiments that approach the fundamental energetic cost associated with information erasure. Related experiments have created information-powered engines in which measurements and feedback allow researchers to extract useful work from fluctuations while keeping track of the complete thermodynamic balance. The results reinforce a remarkably simple statement. Information is physical. But that statement should not be exaggerated. Landauer's principle does not mean that every thought in a human brain has one universal heat cost. Brains are enormously complicated biological systems. Neurons maintain electrical and chemical gradients. Molecules are transported. Proteins are produced and degraded. Synapses change their properties. cells continuously consume chemical energy merely to remain alive. The energy consumed by real biological information processing is vastly more complicated than the theoretical minimum required to erase one ideal bit. The same is true of ordinary computers. Landauer's limit is a fundamental boundary, not a description of the actual energy consumed by every real act of memory or calculation. Still, the connection between information and entropy has profound consequences for the arrow of time. The universe is full of records. A photograph stores information about light that reached a camera earlier. A computer drive contains physical states correlated with previous operations. A footprint preserves information about an object that pressed into the ground. A brain contains physical changes correlated with experiences that have already occurred. Creating, maintaining, transforming, and eventually erasing these records takes place inside physical systems, exchanging energy with their surroundings. Memory therefore cannot be completely separated from thermodynamics. Records are not ghostly descriptions of the past, they are arrangements of matter, and those arrangements exist inside a universe in which entropy is continually being produced. The strange connection discovered through Maxwell's demon therefore reaches far beyond an imaginary creature opening a microscopic door. The direction in which information is written and erased is tied to the same thermodynamic asymmetry that distinguishes the past from the future. To understand why we remember one direction of time and not the other, we must understand what it physically means for the universe to leave a record behind. The second law of thermodynamics is extraordinarily dependable on the scale of everyday life. Heat spreads, gases diffuse, useful gradients fade, entropy increases. But when physicists began examining much smaller systems, they discovered that the arrow of time becomes slightly less rigid around the edges. At microscopic scales, fluctuations matter. A familiar example is Brownian motion. In the early 19th century, the botanist Robert Brown observed tiny particles suspended in liquid moving in an irregular, jittering way. The particles seemed to wander constantly, even when the surrounding liquid appeared completely still. The explanation came much later. The particles were being struck unevenly by the countless molecules of the surrounding fluid. At any particular instant, slightly more molecules might collide with one side than another, pushing the suspended particle in a seemingly random direction. Albert Einstein gave one of the first successful quantitative explanations of Brownian motion in 1905, connecting the visible wandering of small particles to the otherwise invisible thermal motion of molecules. This became powerful evidence for the physical reality of atoms and molecules. It also revealed something important about probability. For a large object, random molecular impacts mostly average away. For a tiny object, they do not. The smaller the system becomes, the more noticeable these fluctuations can be. That means a microscopic system can occasionally move in a direction that appears, for a short time, to oppose the usual thermodynamic trend. Energy might briefly move from a slightly colder region into a warmer one. A small particle may fluctuate toward a less probable state. Over a short interval, an appropriately defined measure of entropy production can even become negative. This does not mean that the second law suddenly stops working. It means that the second law is statistical. The average behavior still points toward increasing entropy, but individual microscopic trajectories can temporarily wander the other way. During the late 20th century, physicists began developing precise mathematical relationships describing these rare events. Important work came from Denny Evans, Deborah Searles, and Gary Morris, as well as Giovanni Gallavotti and Ezekiel Godert David Cohen. Their results became part of a family of ideas known as fluctuation theorems. The central idea can be stated without much mathematics. Suppose a tiny system is driven away from equilibrium and follows a particular microscopic trajectory that produces entropy. There is also a corresponding reverse trajectory in which the system behaves in the opposite way and apparently reduces entropy. The fluctuation theorems relate the probabilities of these two possibilities. Entropy-producing trajectories are usually more likely. Entropy-reducing trajectories are less likely. And the greater the amount of entropy involved, the more strongly the probabilities favour the entropy-producing direction. This gives the arrow of time a measurable statistical signature. Further developments came from Gavin Crookes and Christopher Jarzynski. The Crookes fluctuation theorem compares the probabilities of forward and reversed non-equilibrium processes and relates them to thermodynamic quantities such as free energy differences. The Jarzynski equality provides another remarkable connection. It shows that by averaging a particular exponential function of the work performed during many non-equilibrium repetitions of a process, one can recover the equilibrium free energy difference between the initial and final states. The precise mathematics can become intricate, but the physical message is wonderfully simple. Thermodynamics remains meaningful even when individual microscopic experiments fluctuate wildly. Researchers can repeat a small process many times and use the complete distribution of outcomes to recover ordinary thermodynamic behavior. These ideas have been tested in increasingly controlled experiments. Scientists have stretched and unfolded individual biological molecules. They have manipulated microscopic colloidal particles suspended in fluids. They have examined fluctuations in tiny electronic circuits. Nuclear spins have been controlled and driven away from equilibrium. Quantum systems have been prepared, manipulated, and measured in ways that allow forward and reversed processes to be compared. At these scales, the strange possibility of temporary entropy reduction is not merely philosophical. It can be observed. Imagine filming one of these microscopic systems. If the film shows only a very short sequence, it may not always be obvious whether it is playing forward or backward. A tiny particle wandering through a fluid can jiggle either way. But if enough information is collected, physicists can compare the likelihood of the observed trajectory with the likelihood of its time-reversed counterpart. If the trajectory consistently produces entropy, it is statistically more likely to represent the forward direction. If it appears to consume entropy, it becomes increasingly likely that we are watching a rare fluctuation or the reversed version of a more probable process. In that sense, the direction of a microscopic film is not always identified by an absolute prohibition. It can be inferred from probability. This is very different from a shattered glass. A glass contains an enormous number of atoms. To reverse its breaking would require an astronomical collection of fragments, vibrations, air molecules, sound waves, thermal motions, and emitted photons to become correlated in exactly the right way. A microscopic particle may fluctuate unusually for a fraction of a second. A macroscopic object would require countless such fluctuations to cooperate simultaneously. The probability collapses. The reverse event becomes effectively absent from ordinary experience. So fluctuation theorems deepen the second law rather than weaken it. They tell us precisely how rare entropy-reducing events should be. They connect microscopic reversibility with macroscopic irreversibility, and they show that the arrow of time can emerge statistically even when individual trajectories are not absolutely forbidden from pointing the other way. But an important mystery remains untouched. These relations assume that we have already specified a process, an initial condition, and the way the system is being driven. They explain how forward and reverse trajectories are weighted, once those conditions exist. They do not explain why the observable universe as a whole possesses such a consistent temporal orientation. They do not tell us why stars, planets, memories, biological systems, and laboratory experiments all trace their thermodynamic history toward the same lower entropy past. Microscopic entropy can briefly run backwards. The laws allow it. Probability permits it. Experiments can even detect it. What they still do not explain is why the vast universe surrounding those experiments seems to have begun with the arrow already pointing one way. The arrow of time becomes much more difficult to understand when we stop looking at individual laboratories and begin looking at the universe as a whole. Statistical mechanics can explain why a gas spreads out once it begins in a confined state. It can explain why heat moves from hot regions toward colder ones. It can explain why equilibrium is overwhelmingly more probable than a carefully arranged low-entropy condition. But all of those explanations quietly assume something important. They assume that the system begins away from equilibrium. Without that starting point, there is no obvious reason for entropy to increase consistently in one temporal direction. This leads to what is often called the past hypothesis. The basic idea is simple. The universe began in an extraordinarily special low-entropy macrostate. From that unusual beginning, entropy had room to increase. The thermodynamic arrow could then point away from the early universe and toward everything that followed. Ludwig Boltzmann was already thinking along these lines when he tried to connect statistical mechanics with cosmology. If entropy normally increases, then the world we observe today must somehow be related to an earlier condition in which entropy was lower. Modern discussions of the past hypothesis have been developed further by physicists and philosophers, including David Albert. But the idea creates an immediate puzzle. The early universe was extremely hot. It was extremely dense. Matter and radiation were packed together far more closely than they are today. Those conditions might sound like maximum entropy. After all, hot systems usually have high entropy, and a very dense primordial plasma seems much less orderly than the cool, structured universe around us now. The missing ingredient is gravity. When gravity can be ignored, an evenly distributed gas is often close to equilibrium. Once gravity becomes important, the situation changes dramatically. Gravity encourages matter to clump. A nearly uniform distribution of matter can therefore represent a state with enormous potential for further gravitational evolution. The early universe was extraordinarily smooth on large scales. Matter was not already concentrated into countless black holes, dense stellar remnants, galaxy clusters, and other strongly gravitating structures. This smoothness is one of the reasons cosmologists describe the early universe as having very low gravitational entropy. The matter and radiation themselves could be close to local thermal equilibrium, while the gravitational degrees of freedom remained extremely far from their highest entropy possibilities. Evidence for this smooth early state can still be observed today. The most important remnant is the cosmic microwave background. This radiation was released when the universe had cooled enough for electrons and atomic nuclei to combine into neutral atoms, allowing photons to travel much more freely through space. It now reaches us from every direction as a faint background of microwave radiation. Measurements by the National Aeronautics and Space Administration's Cosmic Background Explorer provided some of the first precise observations of its spectrum and large-scale properties. The Wilkinson Microwave Anisotropy Probe later mapped tiny temperature variations across the sky in far greater detail. The European Space Agency's Planck mission produced even more precise measurements. The striking feature is not simply that the cosmic microwave background exists, it is how uniform it is. Its temperature variations are typically only around 1 part in 100,000. That means the young observable universe was remarkably smooth. Those tiny variations were important. Regions containing slightly more matter than average exerted slightly stronger gravitational attraction. Over enormous periods of time, gravity amplified the differences. Matter gathered into larger concentrations. Dark matter formed extended structures. Gas fell into gravitational wells. Galaxies developed. Within galaxies, dense clouds collapsed into stars. Stars produced heavier chemical elements. Planetary systems formed. Galaxy groups and galaxy clusters emerged, and in the most extreme gravitational collapses, black holes appeared. A universe that once looked remarkably smooth became dramatically structured. This is one of the strange features of gravitational thermodynamics. For an ordinary gas in a sealed box, spreading uniformly usually represents movement toward equilibrium. For a self-gravitating universe, clumping can accompany enormous entropy growth. Black holes in particular can possess vastly greater entropy than ordinary matter of comparable mass. So the smooth early universe contained an enormous amount of unrealized thermodynamic possibility. That low entropy beginning also matters for almost everything happening around us now. Stars shine because they are not in equilibrium with the cold space surrounding them. Earth receives relatively concentrated energy from the sun and radiates more dispersed energy back into space. Weather exists because temperature and pressure differences remain available. Chemical reactions proceed because systems contain usable free energy gradients. Living organisms survive because they exploit those gradients while releasing heat and increasing entropy in their environments. Records can be formed because physical systems are continually changing in irreversible ways. Memories can be stored. Photographs can be taken. Fossils can preserve traces of earlier organisms. Light can leave distant stars and eventually reach telescopes billions of years later. All of these local arrows are possible because the universe has not yet reached complete thermodynamic equilibrium. There are still differences to erase. There is still usable free energy. There is still room for entropy to grow. The past hypothesis provides a remarkably effective way of organizing this picture. If the universe began in a very low entropy macrostate, then the direction we call the future is naturally the direction in which entropy increases away from that boundary. But there is an important difference between describing a condition and explaining it. Saying that the universe began with low entropy does not tell us why it did. The hypothesis supplies the special boundary condition required by statistical mechanics. It does not yet derive that boundary condition from something deeper. And the state appears to have been extraordinarily special. In the space of all possible configurations that a gravitating universe might have occupied, the smooth low entropy beginning represents only a tiny range of possibilities compared with the vastly larger collection of highly entropic states. So the central mystery becomes sharper. Why did the universe begin there? Why was matter distributed so smoothly? Why were gravitational degrees of freedom so constrained? Why was there so much capacity for entropy to increase? Some researchers have argued that cosmological models may eventually explain the arrow of time without treating the past hypothesis as an independent fundamental law. Others regard some form of low-entropy boundary condition as unavoidable. There is no universally accepted answer. But the importance of the problem is difficult to overstate. The direction of time experienced in a quiet room today may ultimately depend on the physical condition of the entire observable universe billions of years before Earth existed. The cup cools because entropy can rise. Memories accumulate because records can form. Stars shine because useful gradients still remain. And all of those facts appear to trace backward toward an astonishingly smooth cosmic beginning. Physics can describe that beginning with increasing precision. What it still struggles to explain is why the universe began in such an improbable place at all. Gravity makes the story of entropy considerably stranger. For an ordinary gas in a box, the intuitive picture is fairly simple. If the gas begins crowded into one corner and is then allowed to spread, it moves toward a more uniform state. The particles become distributed throughout the available volume, the pressure evens out, and the system approaches equilibrium. In that situation, uniformity is associated with high entropy. But once gravity becomes important, the logic changes. A self-gravitating system does not necessarily move toward uniformity. Gravity encourages matter to gather together. Imagine an enormous cloud of gas spread almost evenly through space. If gravity were unimportant, that smooth state might already be close to equilibrium. But if the cloud is massive enough for its own gravity to matter, tiny differences in density can grow. A region containing slightly more matter produces slightly stronger gravitational attraction. That stronger attraction pulls in still more material. The region becomes denser, its gravity strengthens further. This process is known as gravitational instability. Over cosmic timescales, small irregularities can therefore become enormous structures. The early universe provides the grandest example. The young cosmos was remarkably smooth, but it was not perfectly smooth. Tiny density variations existed. Under gravity, those slight variations gradually grew. Matter gathered into extended structures dominated by dark matter. Gas fell into gravitational wells. Galaxies formed. Within galaxies, denser regions collapsed into stars. Galaxies themselves gathered into groups and clusters. The once extraordinarily smooth distribution of matter became the intricate cosmic web observed today. At first glance, this might seem like entropy decreasing. Matter that had been spread smoothly through space became concentrated into highly structured objects. But gravitational systems do not behave like a simple gas expanding inside a laboratory box. As matter falls inward under gravity, gravitational potential energy is converted into other forms. Gas accelerates, collisions become more energetic, material heats up, radiation can escape, stars shine, shock waves form. Matter develops complicated internal structure. The surroundings absorb energy, so gravitational collapse can create local concentration while the total entropy still increases. A collapsing star provides an especially dramatic example. Gravity compresses the material into a smaller region, which might sound like increasing order. But the collapse heats the matter enormously, produces radiation, changes the internal states of particles, and can eventually lead to one of the highest entropy objects known in nature, a black hole. The thermodynamics of black holes transformed the way physicists think about gravity and entropy. During the 1970s, Jacob Bekenstein proposed that black holes should possess entropy. This was a surprising suggestion. A black hole was traditionally imagined as a region from which nothing could escape once it had crossed the event horizon. Assigning thermodynamic properties to such an object seemed almost contradictory, but Bekenstein noticed that the behavior of black hole horizons had striking similarities to the laws of thermodynamics. Stephen Hawking later discovered that quantum effects allow black holes to emit thermal radiation. This Hawking radiation means that a black hole has a temperature. Once a temperature exists, the thermodynamic connection becomes unavoidable. Black holes have entropy, and the remarkable part is how that entropy is measured. For ordinary objects, we often imagine entropy as depending on all the microscopic possibilities contained throughout a volume. For a black hole, the entropy is proportional to the area of its event horizon, not the volume inside it. The area. This is one of the deepest clues in theoretical physics, connecting gravity, quantum theory, thermodynamics, and information in a way that is still not completely understood. The larger the event horizon, the greater the black hole's entropy, and black hole entropy is enormous. A black hole containing roughly the mass of the Sun possesses vastly more entropy than the Sun itself. Supermassive black holes, containing millions or billions of solar masses, dominate many estimates of the entropy stored in the observable universe today. So the growth of cosmic structure is not simply the universe becoming more organized. From a thermodynamic perspective, gravity opens access to extraordinarily high entropy states. This makes the smoothness of the early universe even more important. Roger Penrose has emphasized this through an idea known as the Weyl curvature hypothesis. In general relativity, space-time curvature can be separated conceptually into different components. The part described by Weyl curvature is associated with tidal gravitational effects and gravitational degrees of freedom that become especially dramatic around structures such as black holes. Penrose proposed that the very early universe possessed unusually low Weyl curvature. In simple terms, its gravitational field was highly constrained. The early cosmos was smooth. It was not filled with enormous black holes, violent gravitational distortions, and strongly clumped matter. That smooth condition represented a remarkably special gravitational state. The later universe looks almost like the opposite. Galaxies have formed. Clusters contain vast concentrations of matter. Stars have collapsed. Black holes occupy the centers of galaxies. Space-time contains far more complex gravitational structure. From this perspective, the thermodynamic arrow is closely connected with the release of previously constrained gravitational possibilities. It might be tempting to say that the expansion of the universe causes the arrow of time. After all, the universe expands toward what we call the future, and entropy generally increases in that same direction. But the relationship is not so simple. Expansion changes the conditions under which matter evolves. It allows radiation to cool. It gives density variations time to grow. It creates opportunities for stars and galaxies to form. But expansion alone does not explain why the universe began in a low entropy state. An expanding universe could, in principle, begin in many different gravitational configurations. Simply knowing that space becomes larger does not tell us why the beginning was so smooth. Researchers have therefore explored whether gravity itself might generate something resembling an arrow without requiring the usual low-entropy boundary in quite the same form. Julian Barbour, Tim Kozlowski, and Flavio Mercati have studied simplified gravitational models in which a quantity related to structural complexity increases away from a central state of unusually low complexity. In such models, two groups of observers on opposite sides of that central state could each identify increasing complexity as the direction toward their own future. This is a fascinating possibility, but it remains part of an active and debated area of foundational physics. It should not be confused with the far better established thermodynamics of black holes. Black hole entropy and Hawking temperature are central results in modern theoretical physics. Using gravity to derive the complete cosmic arrow of time is a much less settled problem. Part of the difficulty is that defining entropy for an entire gravitating universe is far harder than defining entropy for gas in a box. There may be no simple external boundary. Gravity itself changes space-time. The universe expands, black holes form and evaporate, quantum effects become relevant, and the meaning of the total number of accessible gravitational microstates is not known in the same detailed way as it is for simpler thermodynamic systems. Still, gravity clearly changes the puzzle. Without gravity, the smooth early universe might look almost maximally ordinary. With gravity, that same smoothness becomes extraordinarily special. The structures surrounding us today exist because gravity had room to amplify tiny differences and release enormous amounts of thermodynamic possibility. Galaxies, stars, and black holes are therefore not exceptions to the growth of entropy. They are part of it, and once again the direction of time seems to trace back toward the same remarkable fact. The universe began in a gravitational condition that left an astonishing amount still available to happen. The thermodynamic arrow is the most familiar way of giving time a direction. Entropy increases, heat spreads, useful gradients fade, records accumulate. But thermodynamics is not the only place where nature appears to distinguish between past and future. There are several different phenomena that physicists describe as arrows of time, and one of the deepest questions is whether these arrows are truly independent, or whether most of them are different expressions of the same underlying asymmetry. Consider light. Switch on a lamp, and electromagnetic radiation spreads outward. A star emits photons into surrounding space. Drop a stone into still water, and ripples travel away from the point of impact. The disturbance begins in a concentrated region and then expands outward. This behavior is sometimes described as the radiation arrow of time. The interesting part is that the mathematical equations describing waves are often much less particular about direction. James Clerk Maxwell's theory of electromagnetism allows solutions corresponding to radiation spreading away from a source. But suitably constructed reverse solutions are also possible. In the reversed picture, radiation would arrive from many directions with extraordinary precision, converge upon one location, and become absorbed in exactly the right way to reconstruct an earlier state. Imagine every ripple on a pond travelling inward from the shore, meeting at precisely one point, and somehow launching a stone upward into your hand. The equations can accommodate the reversed motions under appropriate conditions. The universe simply does not normally arrange the incoming waves required to make them happen. Once again, boundary conditions matter. Something similar appears when we think about cause and effect. In everyday life, causes come before the effects we can observe. You strike a match, and then it burns. A glass hits the floor, and then it breaks. A star explodes, and radiation from the event later travels through space. This causal arrow is partly connected to the causal structure of space-time described by Albert Einstein's theory of relativity. Relativity restricts which events can physically influence one another. Signals cannot simply propagate arbitrarily between every pair of events. But causal structure alone does not explain the full everyday asymmetry. The reason we can identify a past cause is often that the event has produced records. Light has travelled away from it. Sound has spread. Matter has changed. Memories have formed. Those record-forming processes are themselves thermodynamic. Quantum physics introduces another apparent arrow. A quantum system can begin in a coherent state containing several possible alternatives. When the system interacts with a measuring device in its environment, we observe stable records associated with particular outcomes. In ordinary experience, we do not see those records spontaneously disappear while the system reconstructs the delicate original quantum coherence. An important part of understanding this behavior is quantum decoherence. The physicist Heinz-Dieter Zeh was one of the pioneers of this idea, and Wojciech Zurek developed it extensively. Decoherence occurs when a quantum system interacts with its environment. Suppose a microscopic object can exist in a coherent combination of alternatives. Once it interacts with surrounding photons, air molecules, thermal radiation, or a measuring device, information about those alternatives becomes distributed into correlations between the system and its environment. The relative phase information required to observe interference has not necessarily been fundamentally destroyed. Instead, it has become spread through an enormous environmental system. Recovering it would require controlling all those correlations with extraordinary precision. For macroscopic systems, that becomes effectively impossible. The result is that quantum alternatives stop producing observable interference in the ordinary way, and the world begins to look classical. This gives decoherence an apparent direction. A relatively simple, weakly entangled state develops into a vastly more complicated pattern of correlations. The reverse process is permitted by the underlying unitary quantum dynamics in principle, but it would require an extraordinarily special arrangement of the environment. This sounds familiar because it closely resembles the thermodynamic problem. The arrow of decoherence may depend on the assumption that relevant systems and their environments begin with comparatively low correlations or low entanglement. If they instead began in precisely coordinated states, reversed behavior could become possible. Decoherence therefore explains why quantum interference becomes inaccessible in realistic environments, but it does not by itself solve every aspect of the quantum measurement problem. Different interpretations of quantum mechanics disagree about what, if anything, occurs beyond decoherence when a particular result is experienced. There is also a cosmological arrow. The observable universe is expanding. Distant galaxies are, on average, moving away from one another as the scale of space increases. The universe was hotter and denser in the past, and is cooler and more expanded today. It is tempting to identify expansion itself with the direction of time. But that would be too simple. Imagine a hypothetical cosmological model in which expansion eventually stopped and the universe began contracting. It does not automatically follow that shattered glasses would reconstruct themselves during contraction, or that people would begin remembering what we currently call the future. The thermodynamic arrow depends on entropy and boundary conditions, not simply on whether cosmic distances are increasing or decreasing. Expansion affects thermodynamics enormously, but the two arrows should not be treated as identical. Living systems provide yet another apparent direction. Organisms develop, cells divide, embryos grow into mature organisms. Bodies metabolize nutrients, repair damage, reproduce, age, and eventually cease functioning. Biological evolution also produces a historical record in populations over generations, but biology does not require a separate fundamental law forcing life toward the future. Organisms are non-equilibrium systems. They survive by exploiting energy gradients. Plants use energy from sunlight. Animals consume chemically stored energy. Cells maintain concentrations of ions and molecules far from equilibrium. All of this activity releases heat and increases entropy in the wider environment. The biological arrow is therefore embedded within thermodynamics. These different arrows seem to point together. Radiation spreads outward. Records accumulate. Quantum coherence becomes distributed into environmental correlations. Organisms develop and age. The universe expands. Entropy rises. This remarkable alignment may not mean that nature contains 6 separate arrows all independently agreeing about which direction should be called the future. Many physicists suspect that several of these asymmetries ultimately inherit their direction from the same unusually low-entropy past. A universe that began in a special state provides energy gradients, relatively uncorrelated systems, opportunities for radiation to spread, conditions for stable records, and the thermodynamic resources required for life. The arrows then appear together because they all inhabit the same history. The details are still debated. Researchers continue to investigate whether low initial entanglement helps explain the direction of quantum decoherence, how causal asymmetry relates to thermodynamics, and how cosmic boundary conditions determine the behavior of radiation and information. There is no single universally accepted account connecting every arrow in every context, but the pattern is difficult to miss. Time appears to possess many arrows. Yet when we follow each of them backward far enough, several seem to converge upon the same strange feature. The universe began in an extraordinarily special condition, and from that condition, almost everything we associate with the future seems to point away. One of the strangest features of time is also one of the most familiar. We remember the past. We do not remember the future. Yesterday can leave behind a vivid collection of details, a conversation, a meal, a face, the sound of rain against a window. Tomorrow, by contrast, may be planned, predicted, imagined or feared, but it is not remembered in the same way. That asymmetry feels so natural that it is easy to overlook how peculiar it really is. A memory is not simply a thought floating somewhere inside the mind. In physical terms, a memory can be understood more broadly as a present state that carries information about another event. That definition includes far more than human brains. A photograph is a record. A fossil is a record. Writing in a notebook is a record. A computer drive contains records. Tree rings preserve information about earlier growing seasons. An impact crater records a collision that happened before the crater existed. Light reaching a telescope from a distant galaxy carries information about the galaxy at the time that light began its journey. The universe is filled with physical traces of its past. These records form because events interact with other physical systems. Consider a photograph. Light leaves or reflects from a scene and reaches a camera. Those photons interact with photographic material or an electronic detector. The state of the detector changes in a way that depends on the incoming light. The original scene may later disappear completely. People move away. Clouds change. Buildings are demolished. The light continues travelling. But the camera has been altered. A correlation now exists between the present state of the photograph and an event that occurred earlier. That is the essential physical idea behind a record. Biological memory is vastly more complicated, but it also requires physical change. Experiences alter activity within networks of neurons. Connections between neurons can strengthen or weaken. Patterns of molecular signaling change. Proteins are produced, modified, transported, and broken down. Long-lasting memories can involve changes in synaptic structure and in the way groups of neurons respond together. There is no single tiny compartment in the brain containing a complete miniature recording of the past. Memory emerges from complicated biological processes distributed across neural systems, and all of those processes require energy. The brain must maintain electrical differences across cell membranes. Neurons communicate. Ion concentrations are continually restored. Molecules are moved through cells. Damaged components are repaired and replaced. Stable changes associated with learning must be maintained within living tissue. The brain is therefore a strongly non-equilibrium physical system. It consumes free energy and releases heat. That immediately links memory with thermodynamics. But the connection needs to be handled carefully. It would be too simple to say that memories point toward the past merely because making a memory increases entropy. The remembered event itself does not always have to be a lower entropy event than the later state containing the memory. The deeper asymmetry lies in the entire chain of interactions that allows records to form. A photograph exists because light travelled from an earlier scene into a detector. A footprint exists because an object pressed into a surface and altered it. A scar exists because an injury triggered physical processes that changed tissue. A memory exists because an earlier event influenced sensory systems and ultimately left persistent changes in the brain. Each record is part of a causal and thermodynamic history. The physicists Leonard Mlodinow and Todd Brune examined the relationship between what might be called the psychological arrow of time and the thermodynamic arrow. Their analysis considered idealized physical memories and showed that the alignment between memory and thermodynamic time does not depend simply on assuming that writing every memory must itself dissipate some fixed minimum amount of energy. Even a memory mechanism that could operate reversibly in an idealized sense would still tend to acquire records in the same temporal direction as the surrounding thermodynamic arrow when realistic boundary conditions are considered. That result points towards something deeper than the energy cost of one act of remembering. Memory inherits the direction of the larger physical history in which the memory system exists. To see why, imagine what it would mean to remember the future. A genuine future memory would need to exist physically now. There would have to be some present arrangement of neurons, ink, magnetic domains, electrical charges, or other physical variables that was reliably correlated with an event that has not yet occurred. The universe would somehow need to contain records pointing toward later boundary conditions with the same richness and reliability that present records point toward earlier ones. That is not what we observe. We find an enormous abundance of records extending toward lower entropy conditions in the past. The cosmic microwave background records the state of the young universe. Ancient rocks preserve geological history. Fossils record earlier life. Starlight carries images of earlier astronomical events. Human memories contain traces of experiences that have already interacted with our bodies. What we do not find is an equivalent archive of physical records produced by a highly constrained future state and propagated backward toward us. This also explains the difference between remembering and predicting. You can predict that the sun will rise tomorrow. You can calculate where a planet will appear in the sky years from now. Weather models can estimate future conditions, but these are inferences. They begin with records of the past and present, combine them with models of physical laws, and produce uncertain descriptions of what may happen later. A prediction is not the same thing as a physical record created by the future event itself. Memory points backward because it is built from interactions that have already occurred. Prediction points forward because we use existing information to infer what may occur. The psychological feeling of time passing is more complicated. Thermodynamics alone does not provide a complete theory of consciousness, awareness, or subjective experience. It cannot by itself explain why a second feels the way it does, or why the present seems to move. Those are separate and much harder questions involving neuroscience, philosophy, and fundamental physics. But the direction of memory is far less mysterious once records are treated as physical objects. The past leaves traces because physical interactions copy information into the world. Those traces survive because they become embedded in matter. Brains, photographs, fossils, computer memories, and scars all belong to the same general family. They are present structures shaped by earlier events. Memory therefore does not create the arrow of time. It rides along with it. The reason we remember one direction rather than the other appears to be that the universe itself provides an asymmetric supply of physical records. Behind us lies a vast chain of interactions reaching toward a lower entropy past. Ahead of us lies possibility, not memory. And the distinction between those two directions may ultimately be written not only in the brain, but in the thermodynamic history of the entire universe. Most of the physical processes responsible for the world around us are either symmetric under time reversal or extremely close to it. But there is an important exception. Deep inside the behavior of certain subatomic particles, nature really does distinguish between the two directions of time. To understand how physicists discovered this, it helps to begin with two other kinds of symmetry. The first is called parity. Parity asks what would happen if a physical process were viewed in a perfect mirror, with left and right exchanged. For many years, physicists assumed that the fundamental laws of nature should work equally well in the mirrored version. The second is charge conjugation. Charge conjugation means replacing each particle with its corresponding antiparticle. An electron would be exchanged for a positron, for example, while the other relevant particle properties would be transformed appropriately. For a long time, both of these symmetries seemed deeply natural. Then the weak nuclear interaction began causing trouble. The weak interaction is one of the fundamental interactions of nature. It is responsible for processes including certain forms of radioactive decay and plays an essential role in nuclear reactions inside stars. In the 1950s, Tsung-Dao Lee and Chen-Ning Yang examined the experimental evidence for parity conservation in weak interactions and realized that it had never actually been established. They proposed that the weak interaction might distinguish between left and right. Chen Shurong Wu and her collaborators tested the idea using radioactive cobalt nuclei cooled to very low temperatures and aligned in a magnetic field. The result was remarkable. The electrons emitted during the radioactive decay did not emerge symmetrically with respect to the orientation of the nuclei. The mirror image process behaved differently. Parity symmetry was violated. Nature, at least through the weak interaction, could tell left from right. Physicists then hoped that perhaps a deeper symmetry survived. Maybe the laws would become symmetric again if a process were reflected in a mirror, and every particle was simultaneously replaced by its antiparticle. This combined transformation involves charge conjugation and parity. But even that symmetry turned out not to be exact. James Cronin and Val Fitch, working with neutral kaons, discovered that certain weak interaction processes violated the combined symmetry involving charge conjugation and parity. Neutral kaons are unusual particles capable of transforming between related quantum states before decaying. By studying their behavior with great precision, Cronin and Fitch found a tiny but unmistakable asymmetry. That discovery led directly toward time. Modern relativistic quantum field theory contains an important result involving three transformations together. Charge conjugation replaces particles with antiparticles. Parity reflects spatial coordinates. Time reversal transforms a physical process into the appropriate reversed process. Under broad assumptions used in local relativistic quantum field theory, the combination of all three symmetries is expected to remain conserved. This is known as the combined charge conjugation, parity, and time reversal symmetry principle. That creates an important consequence. If the combined charge and parity transformation is violated, while the full three-part symmetry remains valid, then time reversal must also be violated in a compensating way. In other words, some microscopic processes really can distinguish between the two temporal directions. This conclusion has also been tested more directly. The Baybar collaboration studied entangled neutral B mesons produced using the Baybar detector at the Stanford Linear Accelerator Center National Accelerator Laboratory. Neutral B mesons, like neutral kaons, can transform between different quantum states before decaying. The experiment exploited pairs of entangled particles, allowing researchers to compare carefully defined transitions with the corresponding transitions in which the initial and final states were genuinely exchanged in the manner required by time reversal. This point is important. The scientists were not simply watching a particle decay and then imagining the film played backwards. A genuine test of time reversal symmetry requires comparing physical processes that are related by the precise transformation defined by the theory. The Baybar measurements found different probabilities for certain transitions and their time-reversed counterparts. It was direct evidence that time reversal symmetry is violated in these weak interaction processes. Related studies involving neutral kaons and B mesons have continued through experiments including Bell, as well as particle physics programs connected with the European Organization for Nuclear Research and other major laboratories. So there really is a microscopic arrow hidden in fundamental particle physics. But this does not solve the mystery of the everyday arrow of time. The effect is far too specific. Most processes responsible for ordinary thermodynamic behavior are dominated by electromagnetic interactions and by statistical behavior involving enormous numbers of particles. The molecules in a melting ice cube do not need weak nuclear interactions to spread thermal energy through the surrounding water. Smoke dispersing through a room is governed overwhelmingly by molecular motion and electromagnetic collisions. A shattered glass does not remain shattered because neutral B mesons occasionally violate time reversal symmetry. Even if the tiny asymmetry associated with the weak interaction somehow behave differently, there is no reason to expect fragments of glass to suddenly leap from the floor and reconstruct themselves. Nor would memories begin pointing toward tomorrow. There are therefore two separate questions. One asks whether the fundamental microscopic laws of nature are perfectly symmetric under time reversal. The answer is no. At least some weak interaction processes genuinely violate that symmetry. The other question asks why enormous macroscopic systems throughout the observable universe display a powerful and nearly universal thermodynamic direction in which entropy increases. That question remains much harder. The weak interaction asymmetry may have profound cosmological importance. Violations involving charge conjugation and parity are among the ingredients relevant to attempts to understand why the observable universe contains much more matter than antimatter. But the known violations are not sufficient on their own to explain the observed matter-antimatter imbalance, and they have not replaced the low-entropy past as the central explanation for ordinary thermodynamic irreversibility. So there is a curious contrast. At the smallest scales, nature does contain processes that genuinely distinguish past from future. Yet the arrow we experience when coffee cools, bodies age, memories form and stars burn appears to arise mainly from somewhere else. The microscopic laws are not perfectly time-symmetric after all. But the small corner where that symmetry truly breaks is not the reason yesterday stays behind us. By this point, the shape of the problem becomes much clearer. Physics can explain why entropy tends to increase. Statistical mechanics shows that when a system begins in a low entropy condition, there are usually vastly more microscopic ways for it to evolve toward equilibrium than away from it. A gas spreads, because there are enormously more arrangements in which its molecules occupy the available volume than arrangements in which they all remain confined to one small region. Heat flows from hotter regions toward colder ones because equilibrium corresponds to overwhelmingly more microscopic possibilities than a large temperature difference. None of this requires each particle to know which direction the future lies. The behavior emerges statistically. And yet one central question remains. Why did the universe begin in the kind of state that allowed this statistical tendency to point consistently in one direction? The second law of thermodynamics cannot completely answer that question by itself. To say that entropy increases toward the future already assumes that there was less entropy toward the past. The law describes what happens once an appropriate boundary condition is supplied. It does not automatically explain where that boundary condition came from. This is the deepest unresolved part of the arrow of time problem. One possibility is connected with cosmic inflation. Inflation is the idea that the very early universe experienced a period of extremely rapid expansion. It helps explain several striking features of the observable cosmos, including its large-scale uniformity and the origin of the tiny primordial fluctuations from which galaxies later developed. At first, inflation might seem to explain the smooth low-entropy beginning, but the situation is not so simple. Inflation itself requires particular physical conditions in order to begin. A suitable field must occupy an appropriate state. Its energy must be arranged in the right way. And depending on the model, those initial conditions may themselves require explanation. Inflation can push the entropy problem further back without necessarily removing it. This has encouraged physicists to consider more radical possibilities. Sean Carroll and Jennifer Chen proposed a cosmological picture in which a much larger universe can continue evolving without requiring one unique beginning of time. In their proposal, a special low-entropy region can give rise to expanding cosmological branches in two opposite temporal directions. Entropy increases away from the central low-entropy condition on both sides. An observer living on either branch would still experience a perfectly normal arrow of time. Each would call the direction of increasing entropy their future. Neither would watch broken glasses reconstruct themselves or memories disappear backward through experience. The arrows would simply point away from the central boundary in opposite directions. A related idea appears in gravitational models explored by Julian Barbour, Tim Kozlowski, and Flavio Mercati. In simplified systems governed primarily by gravity, they identified states of comparatively low structural complexity from which complexity can increase in two directions. Again, observers on opposite sides could each define their own future as the direction in which structure, records, and complexity grow. These models are intriguing because they suggest that an arrow might emerge without assuming one single preferred temporal direction from the beginning. But they remain debated and highly idealized. Other possibilities appear in bouncing cosmologies. Instead of beginning with a singular Big Bang, the universe might pass through a previous contracting phase before expanding again. Some cyclic models imagine repeated periods of expansion and contraction. Quantum cosmology introduces still other proposals in which the beginning of the universe is described by a quantum boundary condition rather than an ordinary classical starting point. James Hartle and Stephen Hawking developed one influential approach known as the Hartle-Hawking wave function, associated with the idea that the earliest universe may not possess an ordinary temporal boundary in the familiar sense. These proposals differ dramatically from one another. Some attempt to explain why low entropy appears naturally. Others attempt to eliminate the need for a conventional beginning. And some merely shift the question into a deeper level of theory. That distinction matters. A theory has not necessarily explained the special initial state simply because it has given that state a new name. If a cosmological model requires another highly unusual condition in order to produce a low-entropy universe, then the original mystery may simply have been relocated. There is also a very strange problem lurking in statistical ideas about eternal equilibrium. Ludwig Boltzmann once considered the possibility that an enormous universe might spend most of its existence near equilibrium, while occasionally producing rare downward fluctuations in entropy. Perhaps our observable region was one such fluctuation. The difficulty is that smaller fluctuations should generally be more probable than larger ones. Creating an entire observable universe filled with galaxies, stars, planets, fossils, memories, and a consistent cosmic history requires an enormous fluctuation. A much smaller fluctuation, capable of creating a single temporary observer with apparently convincing memories, could be statistically easier. Such hypothetical observers became known as Boltzmann brains. The idea is deliberately unsettling. If a cosmological theory predicts that isolated conscious fluctuations are overwhelmingly more common than ordinary observers living inside a genuine low-entropy cosmic history, then something has probably gone wrong with the theory. We do not merely observe ourselves. We observe a vast, consistent external universe filled with records agreeing about a common past. The Boltzmann brain problem therefore acts as an important test for cosmological models involving extremely long-lived equilibrium states. Anthropic reasoning sometimes enters these discussions as well. Perhaps observers can only exist in regions containing suitable energy gradients, stable structures, long-lived stars, chemistry, and enough thermodynamic imbalance to process information. That may help explain why an observer should not be surprised to find themselves in a universe capable of supporting observers. But it does not automatically explain why such a universe exists in the first place. Selection effects can tell us something about what kinds of environments can be observed. They do not necessarily provide a dynamical explanation of the low-entropy boundary itself. And this is where the scientific position remains surprisingly open. There is no settled consensus on whether the past hypothesis should be regarded as a fundamental law-like condition of the universe. It might emerge from a deeper gravitational principle, it might follow from quantum cosmology, it might arise statistically in a larger cosmological structure, it might eventually be replaced by a model in which time and entropy emerge together. Or some future theory may show that the question has been framed incorrectly from the beginning. What is already understood is impressive. Thermodynamics describes irreversible processes with extraordinary accuracy. Statistical mechanics explains why equilibrium overwhelmingly dominates ordinary macroscopic systems. Information theory connects records and erasure with entropy. Quantum decoherence explains why delicate quantum coherence becomes inaccessible in macroscopic environments. Cosmology reveals that the early universe was remarkably smooth and gravitationally special. The mechanisms operating along the arrow are not mysterious in the same way they once were. The origin of the arrow is. Physics can explain why entropy rises if the universe begins with low entropy. What it cannot yet explain, in a way accepted by everyone, is why that extraordinary beginning existed. And so after centuries of work, the deepest version of the question remains open. We understand remarkably well why time behaves as though it has a direction. We still do not fully understand why the universe gave that direction somewhere to begin. A warm drink cools on the table. Light leaves a lamp and spreads across a room. Footprints fade. Bodies age. Memories gather quietly behind the present. None of these things seem unusual because they happen in the direction we expect. They belong to the ordinary rhythm of life. And yet, Beneath that familiarity, physics finds something deeply strange. Many of the fundamental laws describing particles, fields, motion, and quantum states do not clearly insist on the direction we call forward. At the microscopic level, a reversed history can often remain perfectly compatible with the equations. Collisions can be reversed. Trajectories can be retraced. Quantum evolution can preserve information. Electromagnetic waves can have mathematically valid reversed solutions. The laws are often far more indifferent to temporal direction than the world around us appears to be. The difference emerges when enormous numbers of particles are considered together. A macroscopic object contains an almost unimaginable number of microscopic possibilities, and those possibilities are not distributed evenly among the large-scale states we can observe. A gas confined to one small region can exist in many microscopic arrangements. A gas spread throughout all the available space can exist in vastly more. A temperature difference represents a relatively restricted condition. Thermal equilibrium can be realized in an overwhelmingly greater number of ways. This is where entropy enters the story. Entropy is not simply a measure of how messy something looks. A neat-looking object can possess high entropy. A highly structured system can form while total entropy still rises. The more precise idea concerns the number of microscopic states compatible with the macroscopic conditions we observe. Low-entropy states are comparatively special. High-entropy states are overwhelmingly numerous. So when a system begins in a low-entropy condition, the future does not need to be pushed toward equilibrium by some invisible force. There are simply far more microscopic paths leading into the vast regions associated with higher entropy than paths returning toward the restricted state from which it began. That statistical imbalance is powerful enough to create the irreversible world we recognize, but it is not perfectly absolute at every scale. Tiny systems can fluctuate. Over sufficiently short periods, microscopic particles can behave in ways that temporarily correspond to decreasing entropy. Experiments have measured these fluctuations. They are real. But scale changes everything. A single microscopic particle may briefly wander against the usual thermodynamic tendency. For a shattered glass to reverse itself, enormous numbers of atoms would have to coordinate their positions and motions at once. The surrounding air would have to cooperate, sound waves would need to return, thermal energy would need to reconcentrate. Photons that had already travelled away would need to come back in exactly the right pattern. The probability of such a coordinated reversal becomes so fantastically small that for practical purposes it disappears from experience. Maxwell's demon revealed another layer of the same problem. The imaginary creature seemed able to sort molecules and reduce entropy by using information, but information cannot be separated from the physical world. Rolf Landauer showed that resetting information has a thermodynamic cost. A physical memory must be represented somehow, whether through electrical charge, magnetic orientation, molecular structure, or another material state. When information is erased, distinctions between possible physical states are lost from the memory and transferred into the environment. Entropy is produced. That connection ties heat, information, and memory together in a surprisingly deep way. A record of the past is not an abstract shadow floating outside physics. It is a present physical arrangement. A photograph contains matter that was changed by earlier light. A fossil contains structure shaped by an organism that once existed. A crater contains a lasting deformation caused by an earlier collision. A human memory involves physical changes distributed through living neural tissue. Each is a correlation between something that exists now and something that happened before. This is why memory faces the past. Not because the brain contains a separate fundamental law of temporal direction, but because memories form inside the same irreversible physical history as everything else. Events leave records as information spreads into surrounding systems. Those records accumulate on the side of time connected to the lower entropy boundary, and that boundary appears to reach astonishingly far back. The young universe was hot and dense, yet remarkably smooth. Matter had not already collapsed into the richly structured gravitational state we see today. There were no mature galaxies filled with generations of stars, no planetary systems, no supermassive black holes dominating the entropy budget. The tiny primordial variations in matter density had only begun their long gravitational evolution. From that smooth beginning, gravity amplified differences. Galaxies formed, stars ignited, black holes appeared. Heavy chemical elements were created, planets developed, complex chemistry became possible. Living organisms emerged in at least one known corner of the cosmos. And throughout this history, energy gradients were continually used and dispersed. Stars radiated into colder space. Planets absorbed concentrated energy and released more diffuse radiation. Organisms consumed free energy and produced heat. Information became copied into increasingly complicated records. The same broad thermodynamic direction runs through all of it. There is one important exception to the claim that microscopic physics is perfectly time-symmetric. The weak interaction contains genuine time reversal violation. Certain particle processes really do distinguish between temporal directions. This is experimentally established physics. But it does not provide the accepted explanation for why coffee cools, why smoke spreads, why memories point backward, or why broken objects remain broken. Those everyday arrows are still understood primarily through thermodynamics, statistics, and boundary conditions. And that brings us to the part of the story where physics becomes unusually modest. We understand a great deal about how the arrow works. We understand why equilibrium dominates. We understand why entropy increase is statistically overwhelming. We understand how information processing fits within thermodynamics. We understand why small entropy reducing fluctuations can occur while large reversals effectively vanish. We understand that the early universe possessed an extraordinarily special gravitational condition from which enormous entropy growth became possible. What we do not yet understand, in any universally accepted way, is why that condition existed. Why was the early universe so smooth? Why was gravitational entropy so low? Why did reality begin in a state containing so much unused thermodynamic possibility? The second law cannot answer this by itself, because the second law already assumes the very asymmetry that needs explaining. Inflation may help explain aspects of the early universe, but does not automatically remove the need to understand its own starting conditions. Quantum cosmology, bouncing models, gravitational explanations, and other proposals offer possibilities. None has settled the question. So the arrow of time is both familiar and mysterious. Every second of ordinary experience displays it. A cooling planet displays it. A burning star displays it. A beam of light travelling across interstellar space displays it. A memory forming in a quiet brain displays it. Even a breath taken in the dark belongs to the same enormous thermodynamic history. All of these processes appear to be unfolding away from a remarkably special cosmic past. Energy spreads. Records accumulate. Structure forms and changes. Entropy grows. And somewhere behind all of this lies a beginning whose unusual condition made the entire story possible. We live inside the arrow every moment of our lives. physics can describe its path with extraordinary precision. What it still cannot fully tell us is why the arrow was there to point at all.